we had almost finished our discussions on the potentiometric titrations. I had discussed about the acid base titrations. Then we had discussed about precipitation reactions, and then the redox reactions, complexation reactions, and then we had discussed about the change of PFE from 4.3 to 7.2 to 10 within a volume change of 99.9 to 100.1 ml. So, these values are important for the choice of the indicators for the titration also. Usually, we end our discussion on this note by impressing that within a very small change of volume, there is a big change in the potential, especially in all these reactions what we have studied so far. So, the apparatus as such is not very difficult, but it is a very simple potentiometer what we had used in our previous discussions. This slide will show you a simple potentiometer. The resistances are adjusted to measure the slide wire, and then the battery is a source of supply. Battery works and the solutions are kept here, and this is basically a galvanometer, and currents are measured as usual. Now, we will close our discussion on the potentiometer and continue our discussions on the polarography. Now, polarography is a technique used to measure the current when an applied potential is impressed on a solution in which a mercury drop is used falling from a capillary. So, if a steadily increasing voltage is applied to a cell incorporating a large quiescent mercury anode and a minute mercury cathode, it consists of a succession of minute mercury drops falling from a capillary under the gravity. That is the system we are going to describe now. That is, I have a solution, and in the solution I have a cathode and anode. The anode is a big mercury pool to which an electrical wire is connected, and the cathode is a small capillary through which mercury is falling drop by drop. In such a system, the electrolyte is a dilute solution of the material under investigation. That means, it must be contain a species which is electroactive, and then as the mercury drop falls down, the reaction is taking place, and when the mercury drop falls down, there is no contact and between the anode and the cathode. So, the voltage drops to 0, and the electrolyte is a dilute solution of a material under investigation in a suitable medium, that is, it must be an aqueous solution or a non-aqueous solution depending upon the choice, and it must contain an excess of indifferent electrolyte. That means, an electrolyte which does not get reduced either at the anode or at the cathode. That means, the electrolyte components, cations and anions, do not get reduced, and the only reducible species is in the solution. So, we call it supporting electrolyte, and this supporting electrolyte carries the bulk of the current and raises the conductivity of the solution, thus ensuring that the material to be determined, if charged, does not migrate to the dropping mercury electrode. So, if we look at this slide, we can see that we can examine the current voltage curves and then nature and concentration of the analyte may be obtained. Now, all this is in the system what I had described to you earlier, that is a steadily increasing voltage is applied to a cell incorporating a large quiescent mercury anode and a minute mercury cathode. It is possible to construct a reproducible current voltage curve. So, when we do this, we can examine the current voltage curves and then deduce information about the nature and concentration of the analyte. So, Herowski and Shibata developed an apparatus which contains this quiescent mercury pool and a dropping mercury electrode, and in which they increase the applied voltage at a steadily increasing rate and simultaneously recorded the current voltage curve. Since these curves are a graphical representation of the polarization of the dropping mercury electrode, the apparatus was called a polarograph and the curves are called as polarograms. That means, current voltage curves are known as polarograms. This is the simple apparatus for polarography. Here I have a solution and then in the solution there is a capillary dipped inside that and the mercury drop is falling. At the bottom I have a mercury solution which acts as the anode. From here I take the electrical current and the mercury drop is falling from here. This is all mercury, blue colored, and that mercury is connected to another electrode. So, this is cathode, this is anode. So, I have nitrogen or hydrogen passing through this solution and there is a means for escaping the dissolved excess gases. This is the basic apparatus for polarography. Similar other designs are like this, essentially same, but more useful conveniently for convenience, and there is not much difference except that the functions are essentially same. This is a conical flask, this is a cylindrical flask, etc., and the nitrogen is being bubbled here, and here it is going through out of the from the space in which the gas is held. Here it is passing out, gas is passing out through the solution itself, and from here also it is going out from the available space. So, the basic apparatus consists of a dropping mercury electrode which is referred to as the micro electrode or indicator electrode. The anode is a pool of mercury and its area is correspondingly very large, so that it may be regarded as incapable of being polarized, that is its potential remains constant in a medium containing anions such as chloride, sulphate, etc., and it forms an insoluble salts with mercury. This acts as the reference electrode, that means the anode acts as the reference electrode whose exact potential is not known, but because it is acting as a quiescent mercury pool and things are not getting reduced there, oxidized as well, and this acts as a reference electrode, but whose exact potential is not known, but it depends upon the supporting electrolyte concentration. So, the polarization of the cell is thus governed by the reactions occurring only at the dropping mercury electrode, that is DME. In inlet and outlet tubes, as you have seen in the previous figures, these figures are provided for inlet and outlet tubes, and these are provided for purging the dissolved oxygen by hydrogen or nitrogen before the experiment. Otherwise, the current voltage curves for oxygen are also obtained, dissolved oxygen, because many of the solutions contain some amount of dissolved oxygen. The oxygen gets reduced in such situations. So, dissolved oxygen we do not want in the system. So, other systems will remain the same. That means, we have a potentiometer by which up to 3 volts can be applied to the cell. So, I will have a shunt for adjusting the sensitivity of the galvanometer, that is G. The current voltage cathode, the current cathode curve is recorded with reference to the anode, either mercury pool or with another reference electrode such as saturated calomel electrode. The initial potential of the dropping mercury electrode is indeterminate. That means, when you are not passing the voltage, the voltage of the dropping mercury electrode is indeterminate. That means, you cannot determine, and it can assume any potential that you apply. When it assumes a potential different from that which it had in the absence of electrical connections, it is said to be polarized. This we have discussed earlier, what is polarization, etc. And now, I want you to consider a simple example, that is, consider a cadmium solution along with sodium chloride in an oxygen free medium. That means, the supporting electrolyte is sodium chloride and the species to be reduced is cadmium, and I have already passed a nitrogen through the solution, and that is it does not have any dissolved oxygen. So, when an external EMF is applied to such a system, 2 phenomena occur. I have written down both the phenomenons in this slide. One is, all the positively charged ions will be attracted to the negative electrode by a force proportional to the attraction of the oppositely charged bodies to each other. It is a very natural phenomenon. All the positive ions will travel towards the negative electrode and negative ions will be traveling towards the positive electrode. So, this phenomenon is a very simple phenomenon to understand, and the second phenomenon that occurs is a diffusing force operates arising out of the concentration gradient produced at the electrode. That means, because it is irreversible, the reactions will not be taking place at the electrode until the only reducible species cadmium reaches the electrode, and because the electrodes because the cations and anions are not reduced, they remain near the electrode, forming a sheath of a resisting force, a concentration through which cadmium has to migrate to the electrode to reach the electrode and get reduced. So, a diffusing force is operative with respect to cadmium. So, the diffusing force arises out of concentration gradient produced at the electrode. So, the total current passing through the cell can be regarded as the sum of these two factors. One is electrically oppositely charged particles, another is current due to diffusing force arising where the electrode where the electroactive species will be passing through where the electroactive species will be passing through a concentration gradient until it reaches the electrode. So, the total current is the sum of these two factors, and a typical current voltage curve I am going to show you in this slide. This is the typical current voltage curve. So, you can see I have plotted current here versus applied voltage, and you can see three different parts of the curve, that is A, B and C. In A, I have written as residual current. In B, it is the half wave potential and it is rising, and in the portion C, the current remains largely unaltered. So, this is the known as decomposition potential. So, the curve at B, from A to B, there is practically no current, that is what we called residual current. And then from the point B, the potential is equal to the deposition potential of the cadmium ions. That is, in this range, the cadmium ions will be depositing, and when they reach the electrode, cadmium ions will be discharged upon the electrode surface to form metallic cadmium, and the metallic cadmium will react with mercury to form amalgam, and then this amalgam will diffuse into the electrode, that is in the dropping mercury electrode, mercury mass of the drop, and then it will fall down. So, consequently, as the electrode, as the electrochemical species reaches the electrode, a rapid increase in the current flowing through the cell will be observed. That is what you are observing here, a rapid increase in the region B. So, at the point C, please look at this slide again. At the point C, I have a flat region. So, in this flat region, from the point C, the rate of supply of cadmium ions from the bulk of the solution to the indicator electrode surface becomes equal to the rate of their deposition. That means, as there is no more diffusing force operative, the ions of cadmium are capable of reaching the electrode in a with a sufficiently faster rate and getting reduced also at the same rate. So, the rate becomes equal to the rate of their deposition. So, at potentials greater than C, the concentration of the undischarged cadmium ions at the microelectrode surface is negligibly small compared to the cell ions in the solution. No further increase in current can be expected after C, because the rate of deposition and rate of travel are all the same. So, with the result that between C and D, the limiting current is now fixed by the rate at which cadmium ions reach the electrode. So, we can, this is the basic apparatus for the polarography, and reducible species is usually cadmium or any other ion. You can replace it by any other ion which can be electrolytically reduced, and instead of mercury pool, you can use a rotating platinum wire also as a polarizable microelectrode. You can just use a platinum wire which is rotating, that is to disturb the ionic shield around it. but the most satisfactory one is the dropping mercury electrode from a head of about 40 to 50 centimeter of mercury. You should remember this figure, that is the height of this figure in this figure from this point to this point is about 40 to 50 centimeters, and the idea of taking large quantity of mercury is to see that there is no apparent decrease in the height of this column due to the falling mercury drops. That is why you should have a big head of 40 to 50 centimeter of mercury from a capillary, and usually the capillary size is 0.05 to 0.5 diameter and about 5 to 9 centimeter long. Mercury should be dropping in small droplets. So, this DME has got several advantages. Its surface is renewable, it should be reproducible, it should be smooth, and which eliminates the passivity or poisoning effects. Mercury forms amalgams with many metals. That is another advantage, because any of the electroactive species what you take, they must get reduced at the mercury, they form amalgams and diffuse into the mercury drop also. And then the diffusion current assumes a steady value immediately after changing the potential. That means, I am physically changing the applied potential and determining the current. So, the moment I change the potential, the mercury will be the potential will take the potential what I apply immediately without any time lag, and it is reproducible. So, the another advantage of the dropping mercury electrode is that the large hydrogen over voltage on mercury renders the deposition of metals such as alkali metals, aluminum ions, manganese ions, etc., which are not easily amenable to platinum microelectrode. For example, if you want to determine aluminum ions and manganese ions, etc., it is not easy to determine with a rotating platinum microelectrode, but it is easy to determine with the dropping mercury electrode. And another advantage is the surface area of the mercury drop can be calculated very easily. All you got to do is take 10 drops of mercury in a beaker and then weigh it, and then assume that each mercury drop is almost spherical, and then calculate how much each drop weighs, and then you can determine the surface area very easily with simple arithmetic. So, these are the advantages of DME, and that is why polarography has become one of the most popular technique for the determination of metals and metallic other non metals also to some extent, and then reducible species. You can do the speciation study, that is in what oxidation state metals are present, you can determine. And then the advantage of DME is it can be worked from +4 to -2 volts with respect to saturated calomel electrode. Above 0.4 volts, it is not usually done, because the mercury starts dissolving and starts giving you an anodic wave. That means, it will give a separate wave for mercury, and at potentials more negative than -1.8 volts, visible hydrogen evolution takes place. That is, hydrogen bubbles will start appearing if the solution is acidic. So, that is also not very advisable. So, by supporting electrolyte also sometimes commences to discharge. By using tetraalkyl ammonium hydroxide or their salts, the range may be extended up to minus 2.6 instead of usual alkali metal salts. For convenience and measurement of the half wave potentials, the anode potential may be measured with a saturated calomel electrode using a salt bridge. One can use salt bridge also. So, early polarigraphs used to work only with a salt bridge and then saturated calomel electrode as a reference electrode. So, let us look at the theoretical principles of polarography. Now that you have seen how a polarograph is looking and what is happening at the polarograph and at the electrodes and anodes, you know the working range of the polarograph. Yes. Then let us look at the theoretical principles. One thing you should understand is what we mean by residual current. Mercury is unique in remaining electrically uncharged when it is dropping freely into a solution containing an indifferent electrolyte. You know that we can use potassium chloride and potassium nitrate, sodium chloride, etc. These are called indifferent electrolytes. That means, they do not get reduced at the electrodes. But even in such cases, a small amount of current will flow before the decomposition occurs. That is why you will see a small rise in the current in the range A to B. That is, if you permit me to go back, this residual current, there is a slight increase. It is not exactly horizontal, but it is slightly increasing. So, this current increases linearly with increased voltage, but it is observed even when extremely pure solutions are used. That means, it is not necessarily arising out of the indifferent electrolyte, but suppose you use very pure solutions, even then you would see a small increase in the current as we increase the potential. Therefore, it cannot be due to any impurities, because you will see the same thing when you use very highly pure chemicals, but it is the residual non-Faradic current. That means, it does not result in the reduction at the electrode, but it is a non-Faradic current. That is why it is known as non-Faradic current or condenser current. This is due to the electrical double layer of positively and negatively charged ions surrounding the electrode, but not getting reduced at the electrode. And the capacity of this double layer varies upon the metal and the potential we apply. Metal means usually mercury. And in practice, traces of impurities present in the indifferent electrolyte do cause certain amount of small and imperceptible currents superimposed upon this condenser current. So, all these are called as put together as residual current, and in practical work this current is automatically subtracted from the total observed current by proper extrapolation. You just have to extrapolate and then subtract from the limiting current to get the decomposition potential. Then you will also see the migration current, that is the migration of the charged particles in the electric field caused by the potential difference existing between the electrode and the solution and by diffusion of the ions. That is migration of the charged particles in the electric field caused by the potential difference and the potential difference exists between the electrode and the solution, and also there is diffusion. Migration current can be made negligible by the addition of large quantity of indifferent electrolyte. That means, let the indifferent electrolyte carry maximum current, and migration current should be a very small part of the total current that is being carried. Under such conditions, practically all the current will be transported by the indifferent electrolytes like potassium and chloride ions if you use potassium chloride, or sodium and chloride ions if you use sodium chloride as the supporting electrolyte. And but they do not get reduced. So, they go and hang around the electrode in forming a sheath of the positive ions at the negative electrode and sheath of negative ions at the positive electrode. So, under these conditions, the reducible species, that is cadmium what we had discussed earlier, or any other species, can reach the electrode only by diffusing through that sheath of the ions, that is by diffusion, but they will not reach the electrode until a particular value is reached. That means, they must have enough force to breach through the wall of the indifferent cations hanging around the electrode. So, we have what you call, once these conditions, under these conditions the potential gradient is compressed. As you keep on increasing the potential gradient keeps on getting compressed around the electrode surface, but it cannot permit the transport of the cadmium ions, that is the analyte in which we are interested. So, the limiting current is solely due to the diffusion current, because the electrolyte does not carry any current. So, whatever current you see, you observe, could only be due to the diffusion of the analyte through the electrical layers. So, this is known as diffusion current. Ilkovic examined various factors governing this diffusion current, and he deduced an equation like this, that is I d is equal to 607 N c d raised to half m raised to 2 by 3 and t raised to 1 by 6. So, this is a practical equation, actually it should be 704, but due to changes in the temperature and other factors, 704 gets changed to 607, and I d is known as diffusion current. I d is the diffusion current measured in microamperes, and N is the number of electrons involved in the reduction, that is, if it is a cadmium ion, 2 electrons are involved. So, N would be 2. If it is lithium ion, it could be N is equal to 1, because there is only one species, and in the case of aluminum etcetera, N would be 3. And the C is the concentration of the reducible species, that is in micromoles per liter in general, and D is the diffusion coefficient of the reducible substance. The units are centimeter square per second, and m is the mass of the mercury flowing through the capillary, that is so many milligrams per second, and t is the drop time. So, we have the exponentials, the diffusion current is raised to 1 by 2, that is square root of the diffusion current, and mass of the mercury is raised to 2 by 3, and drop time, that is the amount of time taken for the mercury to form and fall down, that time duration is t, and it is raised to 1 by 6. We will not go into the derivation of this, but we will try to use this expression for the remaining discussion. Now, you can see a polarogram here, and here the residual current is like this, and then another residual current is like this, and then the polarogram is like this. So, you can see that there is one species is getting reduced here, another species is getting reduced in this range, and again it will reach the limiting current somewhere here, and there is one more species that is getting reduced in this range. So, there are 3 species getting reduced. What we have plotted is current versus the potential versus measured against standard saturated calomel electrode. So, the constant 607 is a combination of several natural constants including the Faraday. The ID and 607 are temperature dependent, and therefore, ID is quoted always at specified temperature, let us say at 25 degree centigrade, 30 degree centigrade, like that. Apart from temperature, the other factors are viscosity, molecular and ionic state of the electroactive species, dimension of the capillary, and pressure on the dropping mercury, etc. So, precise measurement of ID requires temperature control of plus or minus 0.2 degree centigrade. The product m raised to 2 by 3 into T is important because it permits the comparison of different capillaries. Suppose you change the capillary from one specific diameter to another diameter, then the product is important, so that it will govern the actual diffusion current. So, stirring of the solution is not permissible during the measurement, because the drops have to fall under their own weight. So, if you stir the solution, drop time will be different. And now I want to introduce you to another concept known as polarographic maxima. Sometimes current voltage curves of the dropping mercury electrode exhibit pronounced maxima, which are reproducible. I do not know whether I have a figure. Yes, here in this figure you can see that the normal residual current is like this. Sometimes applied potential, it is not actually residual current, it is a polarigram, but you are seeing a sudden jump in the case of A compared to B. This is unnatural, because the actual polarigram is B, not A. So, this sudden maxima, sometimes they vary in shape from sharp peaks to broad rounded humps, which gradually decrease to normal ID curves as the potential increases. So, you may be misled that there could be another reducible species which we do not know. Actually, it is not so. It is just a maxima, spurious maxima. So, for measuring the true ID, the maxima must be eliminated or suppressed. It should not be there in general. So, fortunately, we can do this with the solution of using a small amount of a dye stuff, methyl red and then fusine, etc. You can even use gelatin solution for that matter. And what it does is it forms an adsorbed layer on the aqueous side of the mercury solution interface, which resists compression. This prevents streaming movement of the diffusion layer at the interface, thus reducing the maxima. So, maximas can be reduced either by using this methyl red or gelatin or fusine, etc. These are dyes, actually organic dyes, and they can reduce the maxima, and you can do your normal operation of the polarogram determination. And higher concentration of the suppressor, suppose you use very high concentration, then what happens? is usually suppresses the ID itself. So, it should not be too high, and sometimes we use triton X100, that is a surfactant in the concentration of 0.002 to 0.004%, or you can use even methyl cellulose in 0.005%. So, we know this polarographic maxima are basically spurious ones, and they can be eliminated by using small quantities of the surfactants like triton X100 or methyl red or fusine or gelatin itself, etc. And you should not use very high concentration, because the diffusion current itself will get suppressed. That is not very ideal, because we want to determine the concentration of the unknown substance. So, what is there to know more about polarogram? What is left is half wave potential. Since the solutions studied polaragraphically are very dilute, we can assume that the activity of the cation does not differ from its concentration in the bulk. That means, its activity could be most probably 1, because the solutions are very dilute. That statement we have made when the concentrations are very low, activity is equal to concentration, because activity coefficient would be 1. So, we assume that the concentration of the reducible species even in the mercury drop is very low, and its activity remains 1. So, that we can talk about concentrations in general. So, polarography is basically concerned with the electrode reactions at the indicator electrode, that is DME, involving electron transfer. It has to have electron transfer between the electrode and the analyte. During the reduction of the oxide, electrons leave the cathode, react in the solution with the formation of the equivalent amount of the reductant. Similarly, during the oxidation of a reductant at the anode surface, electrons pass from solution to the electrode and form equivalent of the oxidant. So, look at this reaction. I am going to write a very simple reaction Mn plus Ne minus going to MHg, that is a metal ion with N plus, that is in the oxidation state, going to reacting with electrons to form to get reduced, and that reduced metal is in contact with mercury here. That is what I am going to write in this equation. So, I can write an expression known as EDME, that is potential at the dropping mercury electrode, is nothing but the standard reduction potential E naught minus RT by NF ln metal into mercury concentration divided by the unreduced species, that is Mn plus. Since the current I is limited by the diffusion, I can write an expression like this, that I is equal to K into Mn plus aqueous minus Mn plus with a subscript 0 aqueous. That means, this is at the electrode. So, the actual concentration between the reduced species and at the reduced at the mercury electrode would be a product of a proportionality constant and the current. The current is the proportionality constant of multiplied by the difference between these two. So, where Mn0 aqueous represents the point of contact with the mercury surface. Similarly, for the limiting current, the concentration of mercury at the point of contact becomes very small. That means, it is almost negligible. So, in this equation, in the previous equation, I am going to neglect this and then write only the remaining part. Here I d is equal to m k into m n raised to n plus aqueous, because the other part I am going to neglect. From the Ilkovic equation, k is equal to, this is a very standard expression, the concentration of m in the amalgam is proportional to the current I, or now I am going to talk about the concentration of the metal in the amalgam, that is proportional to the current I is equal to k dash. I am not going to write k here, but I am going to write k dash into metal on mercury. That is what I have written here. So, the concentration of m in the amalgam is also proportional to a similar expression k dash into m h g. The constant k dash is identical to k, except d is diffusion coefficient is replaced by d dash, and k by k dash would be, you can show it by a simple derivation, that k by k dash is equal to square root of d by d dash. These equations I am going to put it in equation number 1, that is, in this equation E is equal to E naught minus R T by N f, and what I have is E d m E is equal to E naught minus R T by N f, because it is cadmium, it is 2, R T by N f ln, no, because it is square root, it is, I have taken it here 2, and then ln d by d dash. I am going to separate the diffusion terms here, and then instead of the concentrations I am going to write this I and I d minus I, R T by N f ln I upon I d minus I. So, if we process this equation further, at the point where I is equal to I d by 2, go back to this equation, I is equal to I d by 2, that means here I d, here I am going to write I d by 2, that is I d minus I d by 2, here I d by 2, I d minus I d by 2 is I d by 2, and here it is I d by 2, that means it log of 1, it becomes 0. So, E d m E is equal to this, and when I is equal to I d by 2, the potential at E half is actually E naught dash. Here it is E half is equal to E naught minus R T by 2 N f ln d by d dash, that should be something similar to standard reduction potential, except modified by the contribution from these terms. So, E d m E is nothing but E half minus R T by N f ln of I d by minus I d by I d minus I. The potential at E half is termed as the half wave potential, and E half is the characteristic constant of any redox system, that is, it could be cadmium ion to cadmium metal, or nickel ion to nickel metal, or any of the standard reduction systems what we have studied in our electrochemical series, and its value is independent of the concentration of the oxidant in the bulk of the solution. The theoretical treatment, so far what we have done is for cathodic treatment. Now, let us consider the anodic wave, where mercury is also getting reduced, and you can prove that a similar theoretical treatment works in the case of cathodic wave. So, the same result we can write it like this: O x, the same derivation I am going to do it in a slightly different fashion now. That is, O x plus N e is equal to reductant oxidant plus n number of electrons, that gets n electrons goes to reduced species. E is equal to E naught plus R T by N f A oxidant. This is a form in which we are more familiar. A oxidant by A reductant, and E is equal to E naught plus R T by N f ln oxidant divided by the reductant, where 0 O refers to the concentration at the electrode surface and E refers to the value during the life of a mercury drop. So, the current I at any point on the wave is determined by the rate of diffusion of the oxidant from the bulk of the solution to the electrode surface and under a concentration gradient of O x to O x naught. So, as usual we can ignore the contribution from O x naught, that is on the mercury surface, and we can write K O x is equal to I d, I d is equal to K O x. And when O x naught is 0, I d is simply diffusion current and K is the Ilkovic current. Putting this value of O x naught in the equation 3, what we get is O x naught is equal to I d minus I divided by K. Very simple derivations I am going to give you now. The concentration of the reductant we can also we can consider now on the surface at any value of I should be proportional to the rate of the diffusion of the reductant from the surface of the electrode into the mercury drop. So, I can write I is equal to K into reductant at the mercury surface. So, E I can write, now I have reduced species and the oxidized species in the previous slide. So, I am going to put these values now in the same equation. So, E naught plus R T by N f ln K by K, that is one is capital, another is small, just to differentiate between the reduced species and oxidized species, plus R T by N f ln of I d minus I upon I. So, if you can again as usual you can combine this ln K by K dash capital K by small k. It is only a numerical constant which will affect only the E naught dash value. So, I am going to write it as E naught dash, which includes this number now, plus R T by N f ln of I d minus I upon I. So, when E naught dash is equal to E naught minus K dash, and K dash would be R T by N f ln K by K dash. So, again as usual I do the exercise when I is equal to I d by 2, here I am going to get E naught dash at the this expression reduces to 1 and log of 1 is 0. So, E is equal to E naught dash. So, E is equal to E half at any other value E naught dash half plus 0.0591 upon n, this expression you are very familiar now, into multiplied by log of I d minus I upon I. So, the curve log of I d minus I versus E gives a straight line. If you plot I d minus I versus E, you would get a straight line with a slope of 0.0591 divided by n. So, this number, the intercept would give you E naught dash, where it cuts the x axis, and that is the half wave potential. This equation is termed as the equation of the polarographic wave. It follows therefore, that if log of I d minus I by I is plotted against the potential of the microelectrode, a straight line graph should be obtained with a slope of 0.0591 bar n divided by n. The intercept of the graph upon the vertical axis gives the half wave potential. I am just repeating for your clear understanding, and hence from the slope we can determine the number of electrons involved in the reduction of the species at the cathode, that is n. E half is also known as decomposition potential, because at that potential you can expect the material to reach the electrode easily. The wave should be steeper for higher valence electrons, higher valence elements like aluminum, because it involves n should be 3, and for lanthanum it is 3, cadmium, lead or cadmium it is 2, for alkali metals or thallus ion or lithium ion etc., it should be 1. So, the steepness of the curve is also dependent upon the number of electrons. Therefore, if the reaction at the indicator electrode involves complexation apart from just normal reduction, then satisfactory polarograms can be obtained only if the dissociation of the complex ion is very rapid. There is no compromise on that front as compared with the diffusion rate, so that the concentration of the sample ion is maintained constant at the electrode surface. That is a very important concept. Otherwise, you will not be able to do the complex analysis unless the complex also gets reduced immediately and moves into the bulk of the system, bulk of mercury drop. So, for now we can consider a complex ion then. The complex ion is represented as mxp raised to n minus pb plus going to mn plus and pxb minus. This pxb minus is the ligand, and p is the number of moles, and n minus pb is the charge on the complex ion. For this I can write an instability constant. K instability is equal to the products on the right hand side divided by the left hand side, that is mn plus into x raised to b minus whole raised to p divided by mxp n minus pb plus. This is the very simple expression. All chemistry students would be knowing this expression. Then we can write the equation like mxp raised to n minus pb plus ne plus hg going to metal getting reduced to the metal on mercury and releasing the ligand px raised to b minus, and hence E half we can incorporate as the K instability constant plus remaining part, that is minus 0.0591 upon n into log of x raised to b minus whole raised to p. We will continue our discussion on the complexation reactions in the polarography in the next class.